Thank you, Emilio, for accepting our invitation.
Well, thank you very much for the invitation. Yeah, it's a pleasure to give this talk. So I'm gonna tell you a little bit about the series of works here that I did in collaboration with Apeltim Kavilaj, who's a postdoc at DAISY, and Slava Lichkov, who's at IHOS. And so these works are about random field theories and so-called Parisi and Sourlas supersymmetry. So this, this is the theme, but the plan of the talk is gonna be to give an introduction on CFTs, since I was asked to be very to give a talk for a broad audience. So it's gonna be an introduction, a bit of the jargon, and on the reasons why CFTs are interesting for me, for example, and hopefully this will be good. Also, I will introduce some concepts like renormalization group, DRG, and the bootstrap, which will play some sort of role in the rest of the talk. So this may be useful in general. And the second part of the talk will be about random field models. And I will also be very introductory, will motivate and review most of the time, and then give you a little bit of flavor of what we did in our works. Yeah, these are labeled by 1 and 2, and so this will be for this part and this part. Okay, so this is the plan. So let's start by some introduction on CFTs. So the main motivation why I am personally interested in this is because they are in a very sweet spot because they on one hand they describe actual physical systems, and on the other hand they have a lot of symmetries, and this is not very typical in physics. Sometimes you have a model, and maybe you can write down the model, you can add extra symmetries, but then this model does not describe reality. However, for CFTs, this model do describe reality, and so it's very nice. And the fact that they have such a great amount of symmetry means that you have very powerful tools that you can use, and this is what I'm gonna explain a bit in the beginning, like this bootstrap technique. But let me start by telling you a few words of why these CFTs do describe nature. And so this is the concept of the renormalization group. So I'll be very schematic, but let's imagine that we have a theory that lives on this lattice. So at each side of the lattice, there are some degrees of freedom, and your model is defined by some interactions between these different degrees of freedom. So maybe this model is very microscopical, and instead we are big objects, big observers, and so we don't see these small degrees of freedom. And so what we think is that maybe there's another way to describe the model. For example, if I consider 4 of this lattice side and consider them as if they were just a single lattice side, and I do that for all 4 lattice sides, and I map them to new lattice sides, and the interaction that they were before are mapped to new interactions in the new lattice. And so this gives you a new theory that is defined on a new lattice that lives at a larger scale. And so you can continue doing this process and go to larger and larger scales. And so this is the idea that since we live at larger scales, maybe this is what we actually experience. But the idea is that this procedure is called renormalization group. the idea is that if you follow this until its fixed point, so you continue iterating this procedure, the fixed point should not have a scale because you are increasing the scale at each step. And so in the end, the final theory is going to be scale invariant. So and here is where the CFTs enter. So CFTs are quantum field theories that are also scale invariant. Actually, they have also extra symmetry, which is also there, but one can check that these scale invariant theories that emerge in the IR, they are typically CFTs. And so this is the reason why CFTs appear a lot, is because through this renormalization group procedure, so at very large scales, theories do look like CFTs. And yeah, I mean, there are some disclaimers. These CFTs may be trivial in some cases. In some cases, they may be interesting. But I mean, for this talk, we are going to just focus on interesting ones. And there's another concept that is very interesting that is related to this RG idea, is that so here we started by a lattice description. So imagine that here's your theory in the UV that is a lattice model, and we follow it to a CFT. But while doing this RG procedure, we are in practice integrating out degrees of freedom that are microscopical. And so we are in practice, it's a coarse graining procedure that loses information. And so it doesn't quite matter actually where you start in the UV. You could start with a very different model sometimes, and for example, quantum field theory, so that is defined in the continuum instead of a model on the lattice, and you would flow still to the same CFT. And you can even have a CFT in the UV, okay, perturbed by some deformation, and this would give you all this flow, which, well, in this case would be called the UV complete flow. But you can even study experiments, and in different experiments, for example, you can study boiling water at its critical point, and this would be your experiment 1, and this will be also captured by the same CFT that maybe was defined by your model on the lattice. That is very different, and you could do even different experiment with different materials. For example, a magnet, you study a magnet and study its critical properties, and again you find the same CFT. So this concept is the universality, and so this is a very beautiful concept in physics, and this is telling you that the CFTs play a very important role because they are some sort of equivalence classes for the behavior of different models when you look at them in the IR. And so this is also a reason why CFTs appear in nature. They appear very naturally in many experiments, and also in very different theoretical models. I mean, some of them are on the lattice, some of them are quantum field theories, and so they are really important from like many different points of view. So this was why CFTs appear in nature and why they are interesting. The other point was why CFTs are also a very interesting framework, let's say mathematical framework. And this is because you can apply this kind of bootstrap technique that is and actually mathematically well-defined kind of axiomatic framework that allows you to understand these models and compute observables in these models. So the axiomatic works like this. It's a bit different from what you have in usual quantum field theories, and so it's a different set of axioms, but these are really powerful. And so the idea is that you start by saying that you have a basis of local operators, so these OI, that are inserted at some point x in your space-time. And these operators are labeled by some quantum numbers that are the conformal dimension, which are measured by the dilation operator that is indeed what is the operator that gives you the rescalings. And by rotation, so you have this spin number. So this is like SOD rotations. And you have an important property that is called operator product expansion, or OP, that is an algebraic structure between these local operators that tells you that, I mean, this is very schematic, but the idea is that if you have a product of two operators, you can just replace it by a sum over single operators. And this sum is weighted by these coefficients that are called OPE coefficients. And the idea is that if you put together this dimension and OPE coefficients, this is what you call CFT data. And this set of numbers, just okay, an infinite set of number, but it's still a set of number that defines for you all the local observables in your CFT. And why this is so? This is so because in practice, when you study correlation function of any of these local operators, you can use the OPE iteratively, and you can reduce the number of operator. Let's say you started by n, then you get n minus 1, n minus 2, etc., and then you get to one-point functions. But one-point functions are fixed by symmetry, and so in the end, the point is that with this procedure, if you knew these labels, you could just reconstruct any endpoint function. And so this is what determines a CFT, this set of numbers. And then the question is, then can any set of number define a CFT, or this set of number must be very special? And the answer is that actually this set of number must be incredibly special, because they must satisfy some very strong consistency conditions. And this is what I drew in the bottom. So this you can see them very easily just by this idea. Like, let's consider a 4-point function, so where you insert some operators that I call phi. And now the idea is that you can do this OPE in two different ways, either like doing it with the operator 1, 2, and 3, and 4, or doing 1, 3, and 2, 4. And schematically, this is what happens. So this is the OPE of operator 1 and 2, and 3 and 4, and here is 1 and 3, and 2 and 4. And you see that the result is that you have an equation, and this equation is not trivial. It's actually very complicated, very nonlinear, but must be true. And what appears in this equation are like these OPE coefficients. Then there's a sum over all these operators with these labels. And these objects that here I drew diagrammatically, they are actually some functions that are just fixed by symmetry. They are called conformal blocks. And so they are just, I mean, sometimes you can really write them down in a closed form. They are some hypergeometrics. And so the point is that this equation, then it's a very complicated equation with infinite sums, but you could think of these labels as your unknowns and try to solve for them. Of course, this is really hard, but what it was done is that in 2008, there was a breakthrough in this, and it was found an algorithm to actually put bounds on the CFT data. And the bounds are now like with getting better and better with more sophisticated techniques. And these bounds, which, I must say, these bounds are mathematically exact, then maybe they are not optimal, so you can optimize them. But the point is that this bound becomes so strict that actually determines some of these observables with a huge precision of many, many digits. And so it's a way actually to compute these observables. So it's a completely a new way to think about these theories that is just axiomatical and gives you the numbers and in a way that is mathematically exact. So it's really quite remarkable. Okay, so this was my introduction on CFTs. Now I'm gonna go to the random field part. I will use a bit of this concept, so at least not everything will be wasted. But here I'll start from scratch with some motivation for random fields, unless you have questions about what I said. Okay. So random fields. Why we care about random fields and what are these? So random fields are important. We're introduced to model, let's say, to study models with impurities. So impurities meaning that imagine that we are on this lattice, but some of these nodes are like randomly chosen to be different, for example. And these models with impurities, of course, are really physically irrelevant because in the real world, there are impurities everywhere. So it's really important to understand if these impurities change or not the behavior of your physical system. But another reason why these models with this is random fields is a special kind of impurities, which I will define in a few minutes, but why I'm interested in this special type of impurities is because there was an incredibly beautiful conjecture by Parisi and Sourlas, and so it's just to understand better this conjecture. But here to just give a picture, so like using what I said before, what we are going to study is indeed a CFT, that is the IR fixed point of an RG procedure that then can come from very different parts. Some of them may be models on a lattice, in particular to be like the lattice random field Ising model, but there will be some also random field quantum field theory and even experiments. And they will be all of them will be describing the same CFT. For this talk, we will be mostly interested in the quantum field theory part. So this is the motivation, but since I told you that most of the motivation was this conjecture by Parisi and Sourlas, I should also explain, at least give you a few words of what is this conjecture. So the conjecture is from '79, so it's pretty old, and it's really interesting because it connects very different types of theories. So the idea is that we are studying this CFT, so the IR fixed point here, the IR fixed point of these models with a random field. So for example, the easiest one is the random field Ising model, which we define in D dimension. And what the conjecture is that this is captured by a model with emergent supersymmetry. So this is a model with a supersymmetry of a special type called after them, Parisi and Sourlas. And so this would be Parisi-Sourlas supersymmetric Ising model in D dimension. And so this is already quite remarkable, because it's like finding a model with supersymmetry in nature, so which is quite nice and unexpected. But the conjecture doesn't end there, because this model with supersymmetry would be also captured by a model without supersymmetry in 2 less dimensions. And this would be, in this case, just a pure Ising model, so without any impurities or randomness. And so this is the kind of picture that is quite remarkable. So then, since this is a conjecture, you can test the conjecture, and you very easily see that sometimes it really miserably fails. And this happens, so if you study the random field Ising model, for example, this is defined in dimension 3, 4, and 5, when this critical point exists. And you see that in 3 dimension, it just fails like at order 0, because this model here has a critical point. So it has a phase transition, actually. Well, the Ising model in 1 dimension is very well known not to have any phase transition. And so you are really comparing something that exists with something that doesn't exist. So this is just fails. Then you do it in 4 dimension, and for this it's a bit harder. You actually need to, to check this. You should use this lattice formulation. So you're doing some Monte Carlo simulation on a lattice. So this is a very complicated thing to do, and it was done by these people. And you can check that in 4 dimension, when you study the critical exponents, actually they do not match the ones of the Ising model in 2 dimensions. And so again, the conjecture fails. But however, when you do this in 5D, you see that all the numbers seem to match. And so this is already quite puzzling, because you have a conjecture that sometimes doesn't work and sometimes it works. It's of course easier when the conjecture either works or it doesn't, because you can say that it's wrong or right. But in this case, it's kind of right sometimes, and we don't know why. And this is even weirder, because there's another model. So it's not the Ising model, this random field Ising model. It's another model that I will define later. It's called random field phi cube model. And this is defined from 2 to 8 dimension. And you see that actually in that case, the conjecture works all the time. And so, yeah, the situation is extremely puzzling. I mean, of course, you can do numerical simulation and see when it works, but it would be interesting to have some analytical understanding of why it works in those cases. And so this was our motivation for our work. And what we want to use are some standard quantum field theory methods. So this was the motivation. Now, since I introduced these 3 different models, let me define them quickly. So the first one is the Ising model. So this is the most standard model in statistical physics. So it's defined on some lattice. Well, it's the dimensional, but here I drew just 2D. And at each side of this lattice, you're putting a spin variable that can take the variable, the value plus or minus 1. Then you write down an Hamiltonian that looks like this, where here these spin variables are coupled. You have a sum over all the nearest neighbors. And so this is the simplest statistical physics model. And of course, there's also another description that is also very standard, and is a quantum field theory description. Again, using this idea that you have universality. So if you want here, one would be on the lattice, the other one would be the quantum field theory. And the quantum field theory here is written in terms of this famous 5 to the 4th kind of action. And it's so it has some kinetic term, and then you have a mass term that you want to tune, and this 5 to the 4th coupling. So this is the Ising model. Then what is this random field Ising model? It's very similar. So on the lattice, you can write it like this, where you have the same Ising model part here, but you now have a new term which couples the spins Si to some variables Hi that are quenched random variables. So you want to take them random. So the way you do, for example, you do computations is that you can take some, you can fix some values for Hi, and then these are quenched, so they are fixed. Then you do your computation with those Hi, then you do other computation with a different set of Hi, and so on. And in the end, you want to average over all this possible configuration, considering this this Hi was drawn with some distribution that typically is taken Gaussian. And yeah, maybe I didn't say it well, but this Hi is defined at each point of the lattice. And so you can think of it as a random magnetic field. So at each point of your lattice, you have some, let's say, magnetic kind of some magnetic impurity. And then there's also the continuum the description that it's useful to study this model close to the fixed point, which would be like this. So it's again, in practice, the same as the 5 to the 4th theory, but now again, you want this extra coupling of the field phi with this H, which now depends on continuously on X. And again, you take this H Gaussian with some, and you want it to be uncorrelated in different sites, well, at different position. And so this was the definition of this random field Ising. So that it was this part of these 3 theories. The third one that is missing was this Parisi and Sourlas supersymmetric theory. And so to define it, this is the action. And the action now has a property that is supersymmetric. So you want to define it in superspace. So it's not integrated just in RD, but also in this θ and θ bar, which are Grassmann directions. So in particular, everything here, let's say this field phi, now is also a function of this Grassmann variable. So it's called a superfield. And you can expand it in this Grassmann variable, and it would look like this. So of course, Grassmann variable squares to 0, so you have just 4 components that you can write down. So the first one is called curly phi, and then there are these psi bar, psi, and omega. And here there's an important property for this very special type of supersymmetry, that these fermionic variables, all of them, are actually, I mean, they are just anti-commuting scalars. So they are not spinors, which is actually a bit unfamiliar for people that study supersymmetry in high energy theory. So this is a very special type of supersymmetry that appears in this, let's say, condensed matter systems. And this derivative here, it's like the usual derivative in space-time, but now you have also derivatives in θ and θ bar. So of course, since this action is, you have an integral in θ and θ bar, but you know that integrals in θ and θ bar are equal to derivatives in θ and θ bar, you can actually perform very easily this integration, and you would get an action that looks like this in terms of all these variables. And so it depends on this phi, omega, and psi and psi bar fields. And okay, so this is the model, and so we say that it's supersymmetric, but if people are not familiar with supersymmetry, what is supersymmetry? I mean, for us, for this talk, or for this special type of supersymmetry, the definition is going to be that it's something that maps, it's a symmetry that maps bosons to fermions. And you can see some variations. For example, for this supersymmetry, the simplest one looks like this. It maps this curly phi. So you see this curly phi and omega are bosonic fields, while these are fermionic. And so you want a map that goes from some bosonic to fermionic, and some fermionic to bosonic. And you see that this is exactly the type of map that we have. So you can have this variation of phi that gives you this psi bar, for example, and this variation of psi that gives you some omega, where this is just some parameter. It's a Grassmann parameter for the transformation. And you can just, using these variations, you can really apply them to terms like these. It's quite easy. You would see that the variation would act on these fields like this, and would give you like replacing this with that, and replacing this with this, you get this equation. You get that it's zero. So terms like this are invariant under this supersymmetry. And notice that this term, for example, was indeed this term in the action. So if you repeat it for all terms, you would see that all of them are invariant. And so indeed, you have this supersymmetry. So this is supersymmetric invariant. Okay, so this was the definition of the three models. Now, let me go more to actually our work. So what did we do? So there was this this picture, and so we divided it in two parts. So since this looks very different from, I mean, all these models look very different. So we started by this connection and tried to investigate if this is correct. So since we know that this picture cannot be fully correct because it fails sometimes, we wanted to investigate when it fails. And so we started by this part. And this is called dimensional reduction, because you start by a model in the dimension and you go to d-2. And the idea is that we investigated this with some sort of bootstrapping or some axiomatic type of methods. And so this is what we did for these. And I'll explain it now in a moment, this first part, and then I'll go to the second part later that is going to be about this connection. So we will start by a model with these random fields and get this supersymmetry. And this is going to be studied using a perturbative kind of RG arguments. So now I'll start with the part one. So this is dimensional reduction. So again, it's this part. And the idea is that it always works. So I'm gonna be quick about that. So I just want to give you a little bit the flavor of the argument, but it's in practice this axiomatic type of argument. So we started by a model with this type of supersymmetry. So it's a super conformal field theory with this particular supersymmetry defined by Parisi and Sourlas. And so in these models, we defined, as I said before, you can define the operators, the OPE, you can define the conformal blocks and all of that, and see how this works. And so this is the first step, to define axiomatically what is this theory with this type of supersymmetry. But then we wanted to understand if this theory with this kind of supersymmetry has dimensional reduction. And so, I mean, the first step is, what is dimensional reduction? And so here it's what I mean by that. So imagine that I have this theory that is with this supersymmetry that is defined in d dimension. So in principle, you can study correlation functions of operators inserted in d dimensions. But what you want to do here is putting like all these insertions on a plane that is like RD minus 2. So it's lower dimensional. And the claim is that this correlation function is going to be equal to a correlation function of a CFT in d minus 2 dimension. And so this the reason why this claim works is because there's a very non-trivial decoupling of infinitely many operators, and this decoupling is due to the special supersymmetry. So just to give you more details about it, so here, so using this decoupling argument, we studied dimensional reductions of the operators, and we explained how operators in the bigger theory are mapped to operators in the lower theory. And one thing that is very interesting is that if you study some important operator like the stress energy tensor, that in principle is the operator that measure the energy, and which is a conserved quantity in your theory. So this stress energy tensor is defined in the big theory, and tells you that the energy is conserved there. Now you want to see that what happens under dimensional reduction, and the claim is that there's a stress tensor also in the dimensionally reduced theory, and this is completely non-trivial because this means that energy is also conserved in the lower dimensional theory. But imagine that now we are on this plane. So we knew that on the full space, energy was conserved. But if we now are restricted to a plane, typically we can think that the energy can escape orthogonally to the plane. However, here, the point is that this cannot escape, because you can think of this operator that measures the energies orthogonal to the plane as being one of these infinitely many operators that decouple. And so this tells you that indeed it exists a stress tensor that is conserved in lower dimension. And similarly, you can see how the OPE here is reduced. And also there are like some amazing features due to this supersymmetry that tells you that while in principle you expect that if you have an operator in a higher dimension and you reduce it to lower dimension, you have infinitely many operators. So for each operator in the OPE in higher dimension, you would expect infinitely many operators in lower. You find that all of them decouple but one. So it's quite of a remarkable situation. And finally, we found that the conformal blocks of the theory, in particular the superconformal blocks that you would find in this superconformal theory, are actually equal to the conformal block in two lower dimensions. And this is also explaining axiomatically why this dimensional reduction works. And by the way, I also drew here some very complicated formula just to give you some idea of how this would look like. But the point is that so we found something quite cute, that so this block, which would be this one, is equal to a super block in higher dimension. But it's also known that if you have a super block, you can decompose it in normal blocks, and it just in a finite number of them. And so you find some equations between blocks that, I mean, you can be given this equation without knowing about supersymmetry. And this is just an equation that is true from for some kinematic function. So you have to think that these are some sort of hypergeometric functions. And you find that this very complicated equation is just true. And it's quite of a beautiful result, and it's due to this supersymmetry, but it works in general. So these conformal blocks are, again, just kinematic functions for conformal field theories. And so this was just this first part to tell you how this dimensional reduction, how we studied this dimensional reduction. Now, let me tell you a little bit about this other connection. So how we got this emergence of supersymmetry. So this emergence of supersymmetry is a bit more complicated, and we cannot do it in this axiomatic language yet. And so here, this connection that looks short, now it's gonna be like this one. So it's quite longer. So it has a few steps to follow. So these are the steps. So we start by some theory with random field. Then we do something that is called replica trick. That is a trick used like to deal with random fields. And then we are going to use a change of basis called Cardi transform. And then this concept of leaders that I will explain to give you in practice a description of the IR. And in the end, from this description, we will be able to tell if the theory actually has supersymmetry in the IR or it doesn't. So there are quite a few steps, so it's going to be slightly more complicated, but I will be quick and schematic. So the first part is this replica trick. So a replica trick is something that is really it's a standard tool when you have some random fields. And the idea is the following. Imagine that you get this action that is the action that we have. So where here is the potential. Yeah, I told you that what was the random field easy model. It was when you had this potential equal to lambda phi to the fourth. Now I can also tell you what was this random field phi cube model is when you have this potential to be phi cube. And okay, this was your model. And the important thing is that this is not exactly a quantum field theory in the sense that it's a quantum field theory where in the end you have to average over H. So it's some sort of average over quantum field theories. So it's not quite a normal quantum field theory. And so for this reason, you introduce this replica trick that allows you to actually get a normal quantum field theory where you don't have to do any average over some random coupling. And the final result is gonna look like this. So you see, it's very similar to this action. So you have the same type of kinetic term, same type of potential term. However, you have n copies of them. And the important fact is that then this term that was a problematic one is actually replaced by a term that couples all the n replicas. So instead of having this average over H, you're gonna have just a normal coupling. This is just normal coupling. You don't have to average over it. It's actually like related to this H here that is in the Gaussian distribution in practice. And here is the coupling between the different replicas. And this is a nice normal quantum field theory, and so you are happier. However, there's an important subtlety that you should take the limit n going to 0. So it's quite of a tricky kind of model still. But let me give you a slide to tell you how this comes about so that you can have an idea. So the idea is, imagine that you start by this average. So this is the initial thing where you average over this disorder. some correlation function. This would be written as your correlation function at some fixed h, where here you have the partition function at the denominator, and here you have a path integral with some insertion of the operator, and here is your initial action, that would be this one. Now, this kind of result, then you have to average it over h. However, this is very hard because you have 1 over the partition function, which is a very complicated function. So the trick is to multiply by 1, where 1 is this z to the n minus 1 divided by z to the n minus 1, which is 1 independently of the value of n, of course. And the idea is that then you put the numerator together, and in practice, this give you n copies of the original one. So it's going to be like path integral of n field phi I, where this one will be, the original one will be called phi 1, and all the other one phi 2 to phi n. And so you just get n copies here. But then the important thing is that in the denominator, you have something that looks like z to the n. And the trick, which is a bit dirty, is that you take the limit n going to 0, and so this is just 1. And so you can just remove the denominator that was the complicated part. And the trick is that now you have this Gaussian integral that now you can just commute with the path integral, and you can perform this integration here that is just Gaussian. And the result is going to be this, where this is the action that I told you before. And so the result is that by computing this kind of correlation functions, you do get the original one. This looks very dirty. However, it just, in perturbation theory, you can check that at each order, it just gives exactly the same results. And so for what we're going to do, this is going to be enough. So this is the replica trick. So we were here. Now, let me tell you a little bit about this Cardi transform. I will be quick. So the idea is that this replica action has a feature that is not very nice to do RG. So even when the potential is equal to 0, so that it would be like your UV fixed point or your UV description of the theory, it's actually not easy to describe what is the scaling dimension of your field phi. And this, you can see it because in practice, you have some diagonal and off-diagonal term when you write the matrix of phi I and phi j, that like for the propagator of phi I and phi j, you would see that they do not have this. There are some terms that are different if you are on the diagonal or off diagonal, which means if you want that this dimensions is not well defined. However, there's a very simple way to fix it, that is just by like changing the basis of the fields. And this is just a linear map in the fields. So you have this field phi 1 to phi n, and now you introduce new fields that are called this curly phi, omega, and chi I. And this is the map where this rho is just this average from 2 to n, and this omega is this, and chi I is phi I minus rho, where this is defined from I going from 2 to n. And notice that, so here in principle, I'm defining n plus 1 fields. However, these fields chi I have a constraint equation, so they sum to 0. So actually there are n minus 2 of them. So you have 2 fields and n minus 2 fields. So when you write the action in these new variables, and okay, you fix n equal to 0, you can just see that all these variables actually have a good scaling dimension that you can just write down. and so you are happy. And indeed, so this was the idea of the Cardi transform, and with this Cardi transform, you can finally do RG. And how do you do RG? Well, the way to do RG indeed is you need to know the delta of your operators, because you want to write some action that contains all the operators that are invariant under your symmetries, and that have their dimension less than D. And so this is the way you do RG. So you build these operators are called relevant when the delta is less than D, and so you just build your Lagrangian or your action by summing all these terms that are relevant, and from that you can start doing computations. Of course, if you didn't know how to compute the dimension delta, that would be not a good starting point. But with this Cardi transform, now we know how to compute these deltas, and so we are good. Even though, there is a subtlety. So, I mean, let me just show you what are this type of operators that are invariant under these symmetries. Well, in this basis of replica fields are quite easy. So the symmetries here indeed is the permutation Sn of all the replicas. So you have this symmetry of your Lagrangian, and so fields that take, for example, the sum over this phi I to any power k are invariant under permutations, and so they are good singlet or invariant or uncharged operator. And so you can build actions using summing this type of operators and other ones. There's a subtlety, though, that if you study the dimension of these operators, generically, it's not well defined again, because you have terms with different dimension. However, now you can actually write the dimension of each one of them, and in these Cardi variables. And the idea is that there's this procedure that we put out that in practice, to do RG, you should just pick the lowest dimensional term of your operator. So it's what we call the leader piece. So we write it like that. So this is our prescription. And by doing this, putting all together, so we now have a prescription on how to do RG, and we can now apply it. So to apply it, we start with this this first example where we will find Susie, and this is going to happen in 6 minus epsilon dimension for epsilon very small. So this is very standard in RG. You want to study perturbative RG, and to do it, you need to go near the upper critical dimension, and so this would be the dimension. And when you are near this upper critical dimension, you can write down all possible relevant operators and your Lagrangian, and then you pick the leader, and what you get is a Lagrangian that looks like this. So this Lagrangian looks a lot like what I wrote before for the supersymmetric one. Actually, the supersymmetric one, I wrote it back here so that you can see that they are really similar. However, there's a difference because here you have some field chi, while before you had some field psi and psi bar. So these are bosonic and these are fermionic. However, you can really easily see that this field chi enter quadratically. And so there's, if you want, some emergent ON minus 2 symmetry. But since they appear quadratically, there's this very simple idea that they are Gaussian, and that you know how to perform Gaussian integrals, and you know that they give you some determinant to some power. But you also know that this determinant for bosons is the same determinant that you would get for fermions, but inverse. And so in practice, what happens here is that you have n-2 bosons that would be this field sky, but where n is equal to 0, and so it's -2 bosons, are in practice equal to 2 fermions. And so there's a map. This is actually exact. That if you write this type of a path integral with this kind of action, it's the same one with this one. And indeed, the determinant are the same for n going to 0. And so indeed, you can map this Lagrangian to this one, and you recover supersymmetry. And so now there's the part of, so when supersymmetry is not there, and this happens when you are at epsilon that is large enough. And the idea is that when epsilon is large enough, you may have to include extra perturbation that break the supersymmetry. So here are indeed some types of leaders. So far, we just saw like this type of SUSY-writable leaders that look like this, where you have some chi-squared, which you can map to some psi bar. And so they can be written in terms of SUSY variables. You could also have some SUSY null, what we call SUSY null type of variables that would be like chi-I squared, chi-J squared. Yeah, I'm sorry, I didn't tell you here, every time I write it like this, there's a sum in I and a sum in J that should be there. And so these, when you map it to the SUSY variables, is like a square of a Grassmann variable that is 0. And so we call it SUSY null. But there can be also operators that you can write down that look like chi-I to some power k that is larger than 2, that you cannot write at all in terms of these variables. So the point is, are there new perturbations that are relevant of this type? If, for example, if you have something of this type, for sure, the final Lagrangian will not be supersymmetric. This is clearly breaking completely supersymmetry. And so this is what we did. We studied the dimension of operators, of a huge class of low-lying operators. And we found that indeed there's a family of operators that is interesting, that in terms of the replica fields would look like this. These are differences of phi I minus phi j to some power k, which is non-trivial. It's non-zero only for k equal to 4, 6, 8, and all integers. So the lowest dimensional one are going to be f4 and f6, which when you study their leaders look like this. This is a SUSY null operator. It's exactly this one actually. And this one would be the first non-SUSY writable that looks like this. And what we did, we studied perturbatively in this parameter epsilon, the dimension of these operators. And you see that the result would look like this. And this is up to epsilon cube. And this is for f6. And then you want to plot this dimension against space-time dimension. And this would be the lines that you get. And here is the marginality line that tells you that if you cross it, the operator here becomes relevant. And so this tells you that there's a critical dimension, dc, that is between 4 and 5, that where these operators become relevant. And so you finally get this the picture. I'm almost at the end. So the picture is this one. So you have some theory space, if you want, where here you have your UV fixed point, that is some Gaussian Parisi-Sourlas theory. And if you are higher than 6 dimension, you just have this. But when you are in 6 minus epsilon here, you start having some non-trivial RG that you can follow, and it would land you on this blue line that is supersymmetric, is this Parisi-Sourlas type of Ising model. And in particular, if you follow it for epsilon large enough, so this would be epsilon equal to 1, this is the 5D. And it's telling you that in 5 dimension, you have actually, you will flow to this SUSY fixed point. However, when you are on at this critical dimension DC, that is between 4.2 and 4.7, we estimated, you actually have these new relevant operators that break supersymmetry. And so it means that when you flow from the UV, you're actually not gonna flow on the blue line, but on this new yellow line that doesn't have supersymmetry. And so this tells you that in 3 and 4 dimensions, you don't have supersymmetry, while in 5 dimensions, you recover supersymmetry. And this is exactly what it was predicted by Monte Carlo. And you can repeat the same story for phi cube, and you would see that in all dimensions, you do find actually supersymmetry. And so this is, let's say, a quantum field theory argument of how this supersymmetry emerges and when. So here there are just some conclusions. So there were 2 parts of our work. The first part is to define what was this Parisi-Sourlas type of conformal field theories and understand their dimensional reduction. And this was really using some axiomatic bootstrap type of argument. And the second part of the work was to define an RG setup for these random field theories and study the emergence of SUSY, and finding in particular that for the Ising model, supersymmetry should live in this range of dimension, but when the dimension is low enough, you don't have supersymmetry. While in a random field phi cube, you do get supersymmetry for any dimensions. And okay, I think I'm done. Thank you.
Thank you so much for interesting talk, and also I would like to thank you so much for simplifying everything for us to understand easily.
I hope it was understandable. Yeah, thank you.
It is, I think it was understandable. It's like introduction part is like a lecture, I think. And thank you so much for the effort. And are there any questions to our speaker?
Okay, so I will say we have some questions, because should I also give the camera to the speaker?
As you want.
Okay.
Well, in fact, here we are a bunch of people. My name is Andrea. You don't know me. Hi.
Hi. Nice to meet you.
Thanks also from my side. That was very clear. Nonetheless, I have many questions. But I have to select them, I suppose. Maybe a naive basic question. On the first part. On the first part, you say, look, now we have a beautiful understanding based on conformal blocks and bootstrap and everything that explains how the supersymmetric Parisi-Sourlas model has dimensional reduction. However, Parisi and Sourlas didn't do that at all. They did that much earlier and with presumably completely different methods. Are those methods completely superseded, or they are good for different things, or they are, what's the status of that?
So actually, so what we did, so it's in practice, what we wanted to understand, so the difference is that we wanted really to understand how can it be that the CFT has this dimensional reduction. So if you want, we really wanted to focus on this part. While the argument of the argument of dimensional reduction, I want to say that was actually already on quite of a solid ground. we just wanted to review it in particular on the context of the CFT, because what it was done before, it was on the context of the quantum field theory. So it's a quantum field theory with Parisi and Sourlas, so supersymmetry, which would be indeed this one. So if you have a model with this supersymmetry, you can, for example, this model with this phi to the fourth, if you study it perturbatively, you can check that at each order in perturbation theory, if you study Feynman diagrams, for example, all the Feynman diagrams reduce to Feynman diagrams in lower dimensions. Mm-hmm. And this was the type of argument that Parisi and Sourlas had in their original paper. But then there were other arguments later that were a bit more non-perturbative, and like Cardy gave a very nice argument. But still, I would say that for us, it was still like really unclear how could it be that the CFT with this supersymmetry had this dimensional reduction, because a lot of amazing things had to happen. And so we in practice explained how this happens. And indeed, these amazing things happen. So this is the important thing. And I mean, this complicated equation that I wrote down is one of these amazing things that, I mean, it's true that it's a bit more for CFT aficionados. Maybe it's not so easy to appreciate if you are outside of that, but this is really telling you that you have some kinematic functions that are equal in d minus 2 and in d dimension when you take some very specific linear combinations. And this is due to this supersymmetry, and this kind of had to happen. And I mean, nobody ever, I mean, these conformal blocks were studied for many years, and people didn't find such a beautiful relation. But now you say, well, but I want this supersymmetry to give dimensional reduction, so something like this must happen, and you do find it. And so it's quite amazing. And there are a lot of these small things that must happen that we checked. So let's say that this part of the dimensional reduction, so this part is was under control. The part instead of the emergence of supersymmetry, that the original argument by Parisi and Sourlas was one of those arguments that is like of the type doing some approximations that are not under control, we find supersymmetry.
Well, okay, but that argument, I understand completely your talk. You say we have to classify the possible operators when there are more relevant ones. That's that. So that one is completely clear. Yeah,
let's say that the other still, I mean, the way they did it was very different from this way. So we actually, this argument that we used was revisiting an argument that Cardy gave in '84. So this is where this, with this Cardy transform appeared. Sorry, I don't know. Yes, this Cardy transform is in a paper in '84 where he gave some initial type of argument, but he didn't go all the way on classifying all the operators. But we kind of revisited that argument that is very different. So the original work by Parisi and Sourlas didn't use replicas. So it was a different type of argument, but indeed in that case they couldn't say when it was failing. They were just able to say, well, sometimes it may work. So yes.
Maybe a tiny extra question on this final sentence. So we have these operators F4 and F6, which may appear in D = 4. Is it conceivable that if we are lucky enough, that's the only thing that goes through the marginality line at D = 4, and so that there is some enhanced action in the random field model, which is apparently a normal action, but with a weird potential that tunes to 0 the amplitudes of those, and so genuinely makes an extra connection for one specific tuned potential in the D = 4 case? Or
yeah, this is a great question, because it's one of the things that we try to say, indeed, that this blue line still exists, and as you say, if you have some extra tuning, maybe you're able from here to actually reach the blue line. So, or if you want from here, you would actually, by tuning extra operators, you would reach that. And yeah, we think it's possible. Of course, it's a bit tricky, because I mean, we are finding that there are maybe 2 operators, or maybe more, that cross the marginality line. So it's of course, if you have to tune many parameters, this is not realizable on like on some simulation. But apparently now there's Marco Picco, that is is the world leading expert on this, and is working on this problem, and he was finding in 4 dimension, by some extra tuning of the disorder distribution of the field, that there may be a new second order fixed point. And then, okay, whether that is this supersymmetric fixed point, he could not tell yet. But there are some preliminary results that seem like very good and going exactly in the direction that you were saying.
For me,
I think we are done on our side. We put
Okay.
the mic off.
Thank you very much for the questions.
Is there any other comments or questions? Okay, if no, we can thank again our speaker, and I hope your voice is okay. Is okay now after this talk, because you said that you are not.
No, I'm fine. I mean, I have still some nasal type of voice, but yeah, I'm good. Thank you.
Okay, I wish you also get better soon, and
Thank you.
quick recovery, and thank you again for this nice and pedagogic talk.
Thank you for the invitation again. Yeah.
And have a nice day to all the participants, and see you next week.
thank you.
See you.
See you.
See you.